Hello, everybody. Section 5.4 is called Integration Formulas and the Net Change Theorem. Now, that sounds impressive, but the net change theorem is, I must say, it's not one of those wonderful things to be emphasized. In fact, I will make a brief statement about that, and then we'll focus on the integration formulas. So this section 4 is going to be a pretty light section. And so hopefully you can catch some breath here at this on this section, which is section 5.4. Let's get started. All right, so this section has the formulas, which I will list, many formulas. And these are not going to be new because you have all kinds of differentiation formulas. Just write them backwards and you have integration formulas. How nice, huh? And as I said before, the net change theorem is really not a separate statement. And so I will just casually talk about what this means. The key to understanding this net change theorem is this word displacement. Okay, so we'll go over that as we cover this section, which is section 5.4. All right, so you can list a bunch of formulas for integration now and make a list of these, and that would be called a table of integrals. Now, if you pick up in like any calculus book, like in the library or the bookstore, used bookstore, whatever, you'll find a table of integrals in the back of that book. And in fact, you can look up table of integrals on internet, and you can probably find more than 100 formulas of integration, all of which should end with plus c, by the way. All right, so we have talked about this before. This is 1 over n plus 1 x. Remember, you add 1 to the exponent, and the new coefficient will be that new exponent, plus c if n is not -1, and it is the natural log of the absolute value of x plus c if n is -1. All right, so that's good. And by the way, n is any real number here. Okay, so can you tell what this is? The integral or the antiderivative of cosine? Actually, let me just go ahead and write all of these and see if you can come up with this. Okay, yeah, 1 plus x squared dx, 1 over the square root of 1 minus x squared dx. You can write dx on top if you'd like. That's usually how it's written. All right, pause this video for maybe 30 seconds. You should be able to write down the other side of these equations right away. Okay, so this, is sine of x, right? Because the derivative of the sine function is a cosine function. Don't forget the plus c. To get the sine function, you can't have the cosine function, but you should have the negative cosine function, because the derivative will be negative of sine function, which is positive sine, right? E to the x, the easiest integral. Okay, this is e to the x plus c. Okay, again, wonderful, right? And that's because you are using the most natural choice for the base of the exponential functions, which is e, right? If you don't use e, if you have 2 to the x or something, then unfortunately the equation would not be so simple. Do you remember any function whose derivative is 1 plus x squared? You should. That's the inverse tangent of x, right? And then how about 1 over the square root of 1 minus x squared? That was sine, inverse sine x. All right, so you can just keep writing more and more formulas, just because we had all kinds of differentiation formulas. All right, so with that, let's go ahead and try to do some examples. Maybe one example here. What if you have the square root of t, 1 plus t dt? Well, we haven't talked about such a function, right? But with some thought, I think you can see that you can just actually multiply these. This is t to the 1/2 plus t to the 1 plus 1/2, that's t to the 3/2. Okay, so this is what you get. And so that is, let's see, if you add 1 to 1/2, you get 2/3. The reciprocal of that is not 3/2, 2/3, and then x to the 3/2. Okay. And again, I encourage you to mentally, as soon as you think you got the integral, mentally differentiate what you think is your antiderivative and make sure that the derivative is actually this. So in my mind, as soon as I write this, like I said, I've been doing this for like decades, right? Every time, I think ever since I learned calculus, my first semester of calculus class, every time I integrate, I automatically, my mind tries to differentiate this to make sure I integrated this right. So if I differentiate this, I get 2/3 times 3/2 times x to the 1/2, which is this, right? The next one, if you add 1 to this, that's 5/2. The reciprocal of that is 2/5. And then x to the 5/2. Again, I differentiate this to make sure I get this. All right, and I do, so that's fine. And I just write 1 and 4 here. And so this is 2/3. That's 4 to the 3/2 plus 2/5, 4 to the 5/2. So that's the first part. And then if you plug in 1, you get 2/3, 1 to the 3/2 plus 2/5, 1 to the 5/2. Okay. So what is 4 to the 3/2? Remember, 4 to the 1/2 is the square root of 4. That's 2. And so this is 2 to the 3rd, which is 8. Okay. Now again, this is 4 to the 1/2 is 2, and then 2 to the 5th is 32. That's the first part. The second part is 2/3 plus 2/5. That's easy, right? Okay, so I have 16/3 plus 64/5 minus 2/3, and then distributing the negative sign, I get 2 minus 2/5. Let's combine these. That's 14/3. Let's combine these, and that is 62/5. Fractions are annoying, aren't they? All right, so if you want to combine this, you get what is a 70 plus 186, and that's 256/15. Yeah, that sounds right. So that is the answer to that question. Okay, now I mentioned that this net change theorem can be easily understood in terms of displacement, or at least I kind of referred to this. Let me explain what I mean by this. Okay, so the net change, I'm not going to even state the net change theorem because actually it's not worth doing so in my mind, in my professional opinion. All right, let's say S of t is the position function as we had before, and then the derivative is the rate of the change of position. We know this as the velocity function, right? And of course, if you differentiate this one more time, you get the acceleration function, but that's not really important at this point. Okay, so let's say you have interval from A to B. Actually, that's okay, right? And this is time t. Okay, we have the velocity function, and let's say the velocity goes up and down. Okay, that's our velocity. Remember, the area is the distance traveled, right? So over here, if the velocity is always positive, meaning you're going in one direction. Let's say you have the straight line, and this is the positive direction to the right, and then of course, if the velocity is negative, then you mean that you're going to the left, from right to left. All right, so if the velocity is positive, then you're moving in this direction all the time. Then the integral from A to V of the velocity function turns out to be what? Remember, the area representing the change of position. So this will be the distance traveled. In fact, this is one of the first things I mentioned when we started to discuss integral calculus. But now I want you to think about this. What happens if the velocity function becomes negative at some point? Okay, can you describe the motion described here? or expressed by this graph, right? Well, here the velocity becomes negative. You know what happens right here? The velocity is 0. Yeah, so what's happening is the position at A is some initial position. I don't know where it is, but in fact, the graph doesn't tell you where the initial position is. But starting at A, you're here, and then this object starts to go in this direction. And then the velocity starts to decrease, so it slows down until at this point when S of C is 0, and then after that the velocity becomes negative, so it starts to go this way, right? And then somewhere S of B is going to end up here, right? End up somewhere over here. Maybe before you get back to S of A, maybe more than that. So if you have SB minus SA, this is known as the displacement. Okay. And in fact, it could be 0. If you start at S of A and then goes and C seconds later, you're here, and then you start to go back, it's possible that you get back to the same point, or you go beyond the initial point, or you stop before the initial point is reached. And what is determining that position is actually this integral, right? This is this area represents the distance traveled from SA to SC. And then from here to here, it's going in the negative territory. But if this whole integral happens to be 0, in other words, if this area cancels out this part, then you end up with the same position. Okay, so the point is this integral, which is of course S of B minus S of A, right? This is the displacement. It's going to tell you the net change. Remember, the theorem described here in this book is called the net change theorem, and it's got some fancy language which you don't need to worry about. It's basically net change, and the word or the term net change refers to the displacement. In other words, where did you end up with relative to where you started? Okay, that is the net change or the displacement, and it is described by this integral. All right, so net change from A to B is this, where you have A to B, right? And f of t dt is f, oh, I should say the lowercase f is equal to f of B minus f of A, where f prime is lowercase f. In other words, capital F is, as before, an antiderivative, any antiderivative of the lowercase a. Okay, and that was the case, right? This was the antiderivative of this because V was the derivative of S. Okay, so an example here to keep in mind is that f of t is the velocity function, and capital F was its antiderivative, which is not the acceleration, but remember the antiderivative is this function whose derivative is the velocity. So this will be the position function. And that's pretty much the gist, the essential part of what the book calls the net change theorem. Okay, this is all you need to know. Not much else is necessary to understand the rest of calculus. So we'll hold that there. All right, the last thing I want to say before we close section 5.4 is the integrals of even and odd functions. Remember the symmetries associated with these types of functions. Okay, so an even function, can you come up with some even functions? Go ahead and say it. Okay, even functions. What are some examples of even functions? Cosine of x. Yes, that is an even function. Basically, the right and left hand side look exactly the same, right? X squared, that's an even function. Okay. What else? Absolute value of x, that's also an even function, even though that's not differentiable at 0. That's okay, that's still an even function, and it's continuous, right? So here's the thing, if f of x an even function. And by the way, the technical definition of this is f of negative x is still the same as f of x. That gives you the symmetry with respect to the line y is equal to or x is equal to 0. Remember, this is these functions are symmetric with respect to the y-axis. Because of this property, then the integral from negative a to a, so it will be like from here to here, like -5 to 5 or something. This happens to be exactly twice the half, right? Because if you just take half of this, the other half is going to have the exact same integral. So you can use this fact and simply take the integral of one side of it and double it if you want to find the integral from negative a to a, if f is an even function. Not a very hard concept to grasp. Okay, give me an example or several examples of odd functions. Okay, well, since I had sine, maybe cosine function, sine, I mean, we had cosine, so the sine function will do, right? How about x cubed? Okay, and in fact, how about x? All these are odd functions. If f of x is an odd function, the word odd is sort of strange when when it refers to a person, right? If you say, "Oh, that person is odd," that means the person is weird. Okay, but here, odd means something very specific. That is, f of negative x is not f of x, but negative f of x. So here, that x will give you f of x, but the symmetry is that if you pick negative x, the value is negative of f of x. If that's the case, then guess what? The integral from negative a to a of fx dx is, and imagine that I just lost power and I can't finish this video. And in fact, I just pass out and this video is unfinished. All I have to say is this one last thing, and I didn't have time to do that. And nobody is ever recorded anything like this anymore. Can you fill out the answer here? Can you fill in the answer? I think you can, right? Look, this is from negative a to positive a, negative a to positive a. Basically, the sides cancel each other, right? So the answer is 0. And that's something you can keep in mind as well. All right, I think that's it for section 5.4. Do some exercises. Again, learn these things well.